Good morning, everyone. Welcome to Methane Guiding Principles webinar series. I'm Brian Redick, Senior Associate at Climate Investment, a firm specializing in decarbonization investment. I'll be moderating today's webinar. Our two experts, Peter and Camilla, will focus their discussion on the use of downwind methane measurement detection technology used offshore and in challenging environments. Dr. Peter Evans, a senior engineering product owner at BP. He's the technical lead behind the BP aim to reduce methane emissions. Camilla Fassio is an engineer at E&I, where she is responsible for methane measurement and quantification programs. Before handing it over to the presenters, I'll introduce MGP and its resources. Methane Guiding Principles, or MGP, is a coalition that supports companies and countries on their methane journey from intention and strategy to concrete reductions. MGP offers companies high-quality resources, including best practice guides and practical toolkits. I encourage the audience to visit MGP's website, methaneguidingprinciples.org, to find resources and webinar recordings. Please do also follow MGP on LinkedIn for updates. Peter and Camilla will now present, followed by panel Q&A, which will later be open to the audience at roughly 1:30. With that, I'll hand it over to Dr. Peter Evans.
Brian, thank you so much. So, as Brian said, my name is Peter Evans. I work for BP, based out of London. These sessions are, if you like, a digital conversation. So Camilla and I are going to give you some of our viewpoints and some of our corporate experience on this topic. But the most valuable part comes after that, when you raise some questions. So get some chat going, and if there are things that people want us to dive into, we can do that once we've given these brief overviews. So Brian, if you go to the first real slide in the deck. Before we get going into the technology itself, it's probably worth setting some boundaries for today. So we're talking about quantitative measurements with a particular focus on downwind and offshore settings. Methane's an enormous topic. Issues around qualitative measurements, things like leak detection, an enormous topic in its own right. That's a subject for another day. When we're talking about quantitative measurements, this is where we're trying to express the amount of methane coming from a facility, usually in units of something like kilograms per hour. There are different ways in which you can take those measurements, and alongside doing downwind measurements, there's the emergent area of things like satellite technologies. Again, an enormous subject. We'll pick that one up another day. In terms of why you might want to do a quantitative measurement, there's really sort of two killer applications. The first is if you're looking to work out what the emissions are from a specific piece of equipment. And this feeds into things like level 4 of OGMP. But the most common application that we're seeing emergent is where people are trying to do measurements at the facility or at the major component level. And this feeds into the step of reconciliation, or OGMP level 5. And in order to do that, you need to be getting in the vicinity of the facility in such a way that you can look at all of those emissions en masse. And the most dominant technique for that is being used is drones. There are aircraft applications as well, and a lot of what I'll talk about is common to that. If I happen in passing to mention the name of one particular service provider or another, that's purely by chance. There's a whole growing body of companies out there now, and this isn't a sort of plug for any one company or another. So if we go to the next slide, Brian. So in terms of a quantitative measurement, if there is one thing that people online walk away from this presentation taking, is that an instrument or a drone is not a method. The method is a component, is the product of a whole series of components that go into that measurement. And the drone itself is just one part of that. So when someone says they're doing their quantitative measurement by drone, well, they're right, but it's only one part of the story. So if you look at what goes into the method, well, first and foremost, you've got the sensor. And that might either be a methane sensor or a dual sensor that can pick up things like CO2 concentrations as well. It's important at this point that there is a background concentration of methane in the air. So when someone says that a sensor can pick up 2 or 3 or 4 parts per billion in the atmosphere, the real question is, what is its ability to differentiate an elevation of methane from the background concentration? And then you've got to position that sensor downwind of that source. And that's where the drone comes into case. Of course, there's a myriad of drone technologies out there, and again, an enormous subject. But from a methane measurement point of view, it really comes down to either ones which have a rotary blades, so something that's flying more like a helicopter, or fixed wing type applications, and whether or not they're being flown by pilots, so visual line of sight or extended visual line of sight, or those which are capable of going much longer distances beyond visual line of sight, and then how you fly them as the flight pattern. And that might be in a raster formation or in orbits. And all of that is about just positioning that sensor where it needs to be doing the measurement. But in order to turn that measurement into a quantitative value, you then have to back calculate how it's dispersed in the air. That's the dispersion model. And again, there are different sorts out there. The most common you'll hear people talk about is the Gaussian model. A lot of these models are somewhat proprietary to individual vendors. And you put all of those things together, that defines the limit of quantitation, your ability to measure in kilograms per hour at a given distance and under different wind speed conditions. And in order to provide people with the information that they need in a robust way, you need some quality assurance on that. So it's around accuracy, precision, limits of detection, traceability, and for those people who are working towards OGMP, the uncertainty of that measurement as well. So if you go to the next slide in the deck, Camilla's going to pick up a lot of the practical applications that come into actually getting good quality measurements. But what I would like to do is just for a moment or two, just pick up on this wide issue of quality assurance. This is a nascent area of measurement. It's new to the market. There's very limited precise guidance out there at the moment about exactly how, when, and how to conduct your measurements. Alongside understanding, though, how your sensor works and how your drone works, you need to understand it as a system. And a key part of that, or an emergent piece of that, is around controlled releases. This is where there's methane released into the atmosphere, and it allows you to assess your method, not just your instrument, under something approximating controlled but real-world conditions. When we're talking about offshore applications, of course, that's extremely difficult. And at the moment, the majority of quality assurance and controlled release work has been done onshore, a bit like the photograph that you can see on the left-hand side. And that leaves in place a number of questions in terms of what the data quality is like. There are existing issues around real-world repeatability. What happens when you get things like uncertainty introduced by turbulence around the facility? You've got that propagation of uncertainty, the plus or minus on the value that tells you what level of confidence you can put on that number. There is very little standardization in this space at the moment. It's new, it's emergent. There are a number of bodies starting to stand up ways of checking how measurements are being done. But that kind of proficiency testing that those of you who come from other environmental heritage would consider normal is only just starting to really get going. And of course, how you propagate the uncertainties. And a key part for people that are doing offshore measurements in particular is that the emission rate from a facility is very rarely a constant. What you can see in the bottom right-hand corner is a plot of a number of facilities actually over the course of a year. And where in an onshore setting, the challenge is a spatial one, identifying where the emissions come from. In offshore settings, you know where your facility is, but because of differences in production activity, flaring rates, power generation, fugitives, you end up with often quite complicated and broad changes in emissions that can span orders of magnitude. Now, having faced all those challenges, the question is, well, what do you get out of it? And what is the value of doing quantitative offshore measurements? Well, if you go to the last little slide in my part of the deck, Here's a good worked example that my colleague Isabella Stocker published a little while back. What you can see on the left-hand side is a series of quantitative offshore measurements for about 11 sites. And you can see the challenge that a lot of offshore facilities emit very little methane. 9 sites only account for 100 kilograms per hour cumulative. You've got one site towards the far right where it had elevated emissions, but we knew where that was coming from. And that came from the source level measurements. The one of interest is the one that's coloured in yellow, where it accounts for as many emissions as the 9 sites that came before it, but where the bottom-up inventory of measurements couldn't necessarily identify the full rate of emissions that were being observed by the drone. And that's what you see on the right-hand side, where repeat measurements over the space of a year showed that what we were getting from the top-down measurements did not match what was coming from the source. And that warranted deeper investigation. And whilst it's not very easy to see on the sort of image of the plume that's in the middle of the graph, what it identified was there was an additional previously unaccounted for component that accounted for a significant amount of those emissions. It was a vent which was emitting far more than we had hitherto reported it at. And so we could adjust our subsequent reporting going forward to account for that, because the quantitative measurements allowed us to identify it, but also identify how significant it was to our overall inventory. In order to do that, of course, we have to have reliable and practical ways of working. And with that, I'll pass you over to Camilla, who'll talk you through some of their experiences about getting some quantitative measurements up in the air. Camilla, over to you.
Thank you, Peter. And as Brian said, I'm Camilla Fassio. I work in E&I R&D department, and I focused on innovative technologies for methane monitoring. And I will now proceed from Peter's presentation by explaining and presenting some challenges and issues that are encountered when we use drones to execute methane monitoring activities. As Peter mentioned, the drones technologies and method is useful to get the site level emission with good granularity, both in terms of quantification of emissions and also in terms of allocation. Basically, drones are used to create kind of a wall that is perpendicular to wind direction and where methane concentration is highlighted in order to create kind of hotspots maps that together with wind data allows to quantify the flow rate emitted by a certain area. This technology is very interesting, but it presents some challenges, most related to the repeatability of results, the presence of ATEX classified areas, congested spaces, the difficulties to get an interpretation of wind pattern and the fluid dynamic that is developed inside the plant. Brian, if you please go on the following slide. The deployment of drones is generally aimed at reporting. So to be as representative as possible of our emission, we need to try to capture eventual variability in operational condition and emission that occur at our sites. Drones are by nature a spot measurement, since we are able to quantify methane concentration and then calculate the flow rate for a single moment in time. But as Peter said, basically we have a variability in terms of our emissions and also in the operational range of our sites. So it is central to know how our site is operating during the execution of these monitoring activities. And we also need to have kind of a forecast of our site and how it can operate throughout the year to be able to do repetition of monitoring activities and get different operational conditions to have a good representativeness in terms of what we want to report in future. In the next slide, I will present the second issue that we can encounter during these monitoring activities, that is represented by the presence of ATEX classified areas. In all our sites, we have a huge amount of classified areas, and since we use drone technology that is based on commercial drones, we are not able to access with these drones the classified areas, hence we need to stay outside. When we operate drones on shore, we basically have a lot of spaces where we can fly. For example, where there are the roads where the drone is able to fly since they are not classified, and we can create multiple walls in between equipment. And the allocation of emission is easier since we can understand if the emissions are coming, for example, from the unit of storage tanks or the flare or the compressors. When we move offshore, our plants are packed. Equipments are very close to one another since we need to save space on platforms and FPSO, so it is impossible to fly in between of this equipment. For this reason, the allocation of emission to the specific operational unit is more complicated, and this creates kind of a more difficult reconciliation of emission with the level 4 inventory. In the following slide, I will try to discuss the issue that we can encounter with the different environmental conditions. As Peter anticipated, the drone method also integrates the understanding of wind condition at site, since we create these walls with the concentration map, but we need the wind condition to get the actual flow rate that exists at our site. Using weather data that are not collected at site may be not so representative, since the presence of different equipment and congested space can vary the fluid dynamic of air inside our plant, so we will not be so precise in the quantification of flow rate. So it is necessary to deploy a local anemometer to measure wind direction and speed at site, as close as possible to the operational units that we want to measure, so that the wind pattern is not a general one, but it is very precise and local. We may have also some limitations in terms of wind speed at which we can deploy drones. Basically, below 1-2 meters per second, the development of plume it's not good, so it is more complicated to get a good quantification of methane flow rate. While above 10-15 meters per second, it is not safe to fly drones, so it is better to proceed with future flights when the conditions are more suitable to do this quantification. In the end, I will present some operational issues in our next slide that are not directly connected to an oil and gas facility, but more to its location. As you all may know, there are some no-fly zones for drones that are mostly related to the presence of airports or military areas, and so it is forbidden to fly the drones close to them because of safety and security reasons. Our suggestion, if we want to execute this monitoring activity, is to engage the local airspace entities as soon as possible in order to understand if it is possible to get a flight permission to fly our drone in accordance with the actual operations that are done at site. In the end, as we all know, there are some countries that classify drones as dual-use technologies, so they are also classified for military use, hence their import and clearance inside these countries is not easy, and it is often forbidden. For this reason, it is important to try to engage local authorities as soon as possible, and in case it is impossible to get them clear, it is necessary to get a backup solution to do similar monitoring activities as a backup for the drone technology.
Peter, Camilla, thank you both for such an excellent presentation. Certainly a lot to unpack and discuss. So for the next 15 minutes or so, let's kick around some questions between us three. This question might be a little angled towards you, Peter. When do you envisage aerial measurements being covered by recognized standards of operation, like other environmental measurements? You briefly touched upon this.
It's a really good question, Brian, and it's one of those subjects that's very close to my heart. For those who know me, I started out my life on the other side of the fence as a sort of measurement regulator setting standards. Standards are the way that you assure that the data that people are providing can be trusted and used appropriately. They're also the basis on which innovation keeps going, because it says what good is like today and what what things can be improved and how new technologies entering the market can prove themselves as being better, faster, cheaper, whatever else it happens to be. The world of standards around methane are evolving very rapidly, but at where we sit here right today, there are, for any methane measurements, be they source level or facility level or drone measurements, what have you, very few written standards out there at the moment. There are guidance documents, but very few things which are sort of formally in existence in legislature. The first generation of those are really just starting getting going. And there's a number of new ISO committees which have just been stood up to address that, and a number of national initiatives as well to put in place better standardization. But by the very nature of what these things are, the first generation will probably be relatively light touch, laying out the sort of very basics of what go into repeatable, trusted measurements, and they're likely only to emerge over the next 18 months to 2 years. So there is work to do, but by the world of standards, it's happening very quickly. And the best way that these standards move on quickly is making sure that the people that are volunteered or have been tasked to write them have access to as much information of what the state of the art is. So if you are contacted by anybody who's standing on those committees to look for evidence or data, please do contribute, because then it sets out what is going to be possible and what good is going to look like for the next few years.
Thanks so much, Peter. How have you, and this question I think both of you can certainly touch upon, and Camilla, feel free to kick this one off. How have you approached variability in wind and weather when focusing on obtaining high quality survey data sets?
Okay, I can kick it off, and then Peter, you can add whatever you think it's interesting. So for our experience, we executed the monitoring activities with a quite wide difference in terms of wind speed and direction. What we understood is that when the wind is so low, we don't get the plume to develop, as I was saying before. So the measurement is basically useless. So it is better to stop with measuring, since there is kind of stagnation of methane. The plume, it doesn't develop. So it's complicated to get an actual flow rate. So our suggestion is to try to get as much measurement as possible with different wind conditions and also directions, in order to distinguish between different areas that could eventually emit, and then to get the variability of how the plume develops. And then the main issues is evaluating the data once you get them at the end of the execution of the activity, to evaluate if there is something that is totally out of, doesn't make sense with what we expect in terms of emission. And if we know that nothing weird is happening at site, we don't have variability in terms of condition, we need to check our weather condition. And the importance of having an anemometer and the local wind measurement is very high to get precise quantification in the end.
Maybe if I jump in with a little bit that builds on that as well. I mean, Camilla makes a great point about the practicalities of flying. In the presentation that I gave, I was talking about how the emissions vary through time for a facility, and that's one part of the planning process. But most of those variations aren't dictated by time. What happens in summer is basically the same as what happens in winter. But in terms of actually deciding when to fly, thinking about when you are likely to get a good and predictable dispersion from the facility, when the plumes are likely to be stable, is very important. And for a lot of these sensors, well, for any sensor for that matter, they will have an operating range, a maximum and minimum temperature in which they need to operate. And also, just very practical things for people in locations like the North Sea. A lot of sensors don't like operating in the wet, because that changes their ability to function as well. One of the very interesting cases we found is, for a long time, we've always known with any kind of dispersion model, as the wind speeds pick up, the more rapidly that plume gets dispersed and diluted, and the harder it is to measure. One of the very interesting case studies we've had to wrestle with within BP is actually the exact opposite case, where we have one location in the world which is characterized by very, very low wind speeds for the vast majority of the year. The reality of that is if we went out with a normal dispersion type planning approach, we could wait for days, if not weeks, for the wind to pick up before we could take measurements. And what we've actually had to do is look at those dispersion patterns around the facility in much more detail than we would normally, to target precise times of day to do measurement, because there are only certain times in the day when the wind speeds get up high enough in order to get some kind of reliable model, because without which, instead of a dispersion plume, you have something which effectively looks more like a mushroom cloud when you model it, with the methane moving out in all directions, and that's much, much harder to quantify.
Thanks so much. Excellent responses. Peter, in the recent SPE HSE article, you mentioned that Isabel Stalker wrote and you contributed to, right? You mentioned how the data collected followed a fat tail distribution. So what does that say about the value? So you spoke in detail about its value and the need for site level measurement. In the world of US onshore methane detection, we've seen aerial survey companies cover entire key basins multiple times, and it's clear that by volume, methane emissions do follow a fairly skewed fat tail distribution, broadly speaking. Do you think we'll continue to see similar results internationally using these technologies?
It's a good point. I think if there's one thing that has come out of the recent years of people measuring methane and reporting what they're seeing, be it through drones or source level measurements, what have you, is the emissions profiles are complex. And knowing where to target resources is ultimately why we're doing this work. When we're measuring methane, yes, it's important to improve the quality of the data that appears in things in our sustainability reports. But first and foremost, we are measuring in order to know where finite resources can be targeted to achieve the most meaningful mitigations against methane emissions. And in an onshore setting, as I said briefly in the presentation, I think what's come out of a lot of the research is identifying those locations which are anomalies within the fleet. When we go to offshore and large consolidated assets, the emissions profile is equally complicated, but it's more of a variation through time, where a site can go from very low emissions during routine production through to very high emissions if you've got something like a flare, which is operating outside of its planned efficiency window. And it's understanding that distribution, which goes into not only planning the top-down measurements themselves, or the drone-type measurements, but also knowing how representative each one of those measurements is. And being able to identify locations which have entered into that fat tail, if you like, knowing that there is something anomalous on that facility that warrants investigation. And by being able to quantify it, it allows you to compare how it is performing compared to how you planned for it to perform, and how it compares to the peers in your fleet. So you can target the resources into that specific intervention on a quantitative basis, and then having made that intervention, be able to demonstrate the reductions that have been brought about by it. Camilla, anything to add on that one, or there's some great other questions in the chat?
No, thank you, Peter. I think your answer was very complete. And I don't know, Brian, if you want to start with the question, because yeah, I agree with Peter on this.
Great. Hey, thanks so much, Peter. Yeah, so it's a good time to move to Q&A with the audience. Please do type your questions into the text box that you can access by clicking the Q&A button on the top bar here. So let's take a look at some of those questions. I'll read them out, and we can answer them. Let's take a second here.
There was a great one from Mark Harrison who pinged it early into the presentation. It picks up a lot of topics. So I don't know if you can see that one, Brian. It should be right down the bottom of the chat. Or I can read it out.
Oh,
it goes,
please go ahead.
Yeah, so Peter, you mentioned the dispersion model as a key element of the top-down drone deployment. However, it is very reasonable or very possible to do that quantification using only wind speed and concentration data, a flex plane mass balance, without the need to use inversion dispersion modeling. This removes a source of error in modeling. Can you comment on this, please? Oh, that's a great question, Mark, because it brings together what I was trying to capture early on in that presentation about saying that it's when someone says, how have you done your measurement? And someone says, well, I've done a drone measurement. Well, that doesn't tell you anything. It's those combination of factors that go into defining your method that then tells you the limits of confidence that you can put in that data and how you can use it appropriately. And for that, Mark, you clearly understand this, but for those who are newer to this space, there are different ways in which you can handle that dispersion from the facility. And one of them is to do that sort of classic Gaussian plume type inversion, where you measure the wind speed and the concentration, and you try to back model both where it came from and its rate from source. The other way that you can do that, and particularly with things like larger and fixed wing drones, is try to measure the concentration of methane in the air, upwind and downwind of your facility, and look at the mass balance between the two. And again, a perfectly credible way of quantifying your methane emissions. Unlike so many other things in the methane space, there is no silver bullet. There is no perfect solution that fits all scenarios in order to say you should always do it by dispersion modeling or you should always do it by mass balance. The great advantage of mass balance, as you put in your chat, Mark, is it removes that that ambiguity of having to put in some sort of model that looks at how it has dispersed. It's purely a what entered your airspace, what left your airspace calculation. The downside, of course, to that is you have to be able to be looking what's entering and leaving your airspace in pretty quick succession, which often means that's why it lends itself well, for example, fixed wing drones, which are doing orbits around a facility instead of doing raster type flights. Of course, the other factor in terms of if you're doing that is you're invariably flying further away from your facility in order to do it. And certainly in our case, where we've done measurements on things like FPSOs that rotate around the drilling, around the drilling tower, you need to measure a sort of 600, 700, 800 meters away from the facility. You've then got more dispersion. It means you're working with a lower concentration plume, and you might find it harder, having found something that's anomalous, to isolate where it comes from, but your quantification might be simpler. So it's a swings and roundabouts. There's no perfect solution to this. What is important is that when people say how their measurement is done, they can be quite specific as to what type of calculation went into that equation, so somebody who's evaluating it can understand what its advantages and disadvantages are.
Thanks, Peter.
Brian and Peter, if it's fine for you, I can take the following two questions in the chat that are more related to the use of wind speed data. The first one, I don't see who wrote it because it appears to unknown user to me, but they ask, is it possible to use wind speed data from the drone sensor itself instead of on-ground anemometer? Will it be helping in terms of accuracy? And I try to connect it to the following one, always from Matt. For the flux plane mass balance, what is the state of the art on gathering wind speed at each drone location? I will try to combine these two answers since I think it's interesting. So what I presented included the fact that it is important to get local wind data. Generally, the anemometer that is used inside the plant is, of course, not ATEX, so we need to stay outside of ATEX classification zones, and it is generally installed on a tripod, so it is around ground level up to maybe 2 meters high, while, of course, when we want to monitor a wall that is representative of our entire facility, we need to get up to 80 meters up to the flare height, even a bit upper, since the methane is lighter than air, so it flies up. So what some providers do is using the anemometer at ground, and they combine it not with so the sensor does not measure wind speed, but they keep another 1 or 2 anemometers on the drones themselves. So they basically measure wind speed and direction at different heights where they fly the drones, and they kind of create of an evolution of wind speed and direction at height. So this, of course, reduces the uncertainty of the model, since it is more representative of the actual data. So I think this kind of answers also the second question, since the anemometer needs to be moved for each wall that is created at site, so that we have a good representativeness of different locations, and the measurement of wind speed and direction also at different heights allow to see how the wind speed varies at different height and directions also. So we get a more precise model, I think, and then the quantification has better, so lower uncertainty in the end. I don't know, Peter, if you have anything to add here.
Yeah, I mean, I agree with everything you say, and I think the way that wind is incorporated into different services at the moment, it does seem to vary between vendors, and they have different strategies. I think one, particularly thinking about offshore measurements, one of the big questions that sits out there at the moment is around the overall repeatability of the method. And one of the challenges in the sort of controlled release experiments, like the one that I showed a picture of on screen when we were talking, is it's being released from a very simple source. In that instance, we took a massive crane and put the methane source at the top. So at least we were away from the ground. But of course, when we're talking about a large offshore structure, and we're measuring downwind of it, that structure itself creates variable amounts of turbulence and complex wind patterns. So something that's very high, like an exhaust stack or a flare, is experiencing a different wind profile to potentially a vent or a smaller source or a fugitive, which is operating within the plant itself, closer to deck level. If you get very close to a facility, you start getting wake effects where the wind that's happening in that immediate vicinity is very different to if you moved further away from the facility, and those kind of random turbulences have sort of evened out into a more measurement plume. But of course, the further you move away from the facility, the more dispersed that plume gets, and therefore it's harder to detect. And it's understanding and accounting for wind speed within your method, which again is one of these areas of standardization, which is now starting to emerge in conversation, but there isn't a perfect solution to it yet. And I suspect that the exploration of turbulence around facilities and how to and where to position your aircraft or your drone for doing a downwind measurement is going to become a lot more exacting in the next few years, because it's so critical to that overall calculation. Brian, what's your next favorite question on the list?
Let's see. There's a lot of good ones today. So so how about from Ian? I'll read his question out loud. For the use of drones, which are not intrinsically safe, is there any guidance for how risk is managed? For example, any general practices regarding distances away from equipment while still being able to maintain ability to detect emissions and data quality?
I can
Camilla.
kick this off if you want, but
go
I
ahead.
will connect to something that you said. So it still depends on the facility itself, because so if we are operating onshore, maybe on a road that is between two different equipment, we need to keep an amount of safe distance from the equipment on both sides of the drone that is flying. So basically you fly moving horizontally but also vertically, so we keep the distance kind of fixed during the execution of the wall. And we try to stay so in safe area, but at least 10-20 meters from the closest equipment. And for example, if there are any pipe racks that kind of cross this road at a certain height, we try to be at least at 4 or 5 meters from them for safety reasons, so that we avoid just to crash the drone to the on the equipment. So it can create, of course, an hazardous risk. But as Peter was saying before, when we operate offshore, for example, with the FPSOs that are automatically oriented depending on wind direction and also wave direction, we need to get a higher distance from the equipment itself just to be safe. He was talking about like 500 meters, and which is higher, of course, offshore. We need to stay at higher distance. And as Peter was already saying, it can create a issue because like the plumes enlarges with distance, so the concentration is lower, so we are less precise. So it's kind of a trade-off between safety in terms of operation, but also we need to get this data more precise as possible.
And it sounds like we follow a similar strategy to you, that where it's offshore, of course, once you're moving at a distance far enough away to get a decent plume measurement, you're well outside of the safety zone. So we don't have to worry about 8x rating, apart from, of course, when the drone is taking off and landing. And we tend to use the helipads for that, of course. Onshore, where we've got large onshore facilities, for practical reasons, we tend to divide the site up into a series of zones and use the interconnecting roads in it. Sounds like a very similar way to yourself, Camilla, to define the flight path, because of course those roads have a lower rating because you have vehicles moving along them. It also actually turns into just a very practical way of dividing up the site and people knowing exactly which part of the site is being measured, and sort of breaking up a facility into a series of components. Invariably, the roads tend to work around major equipment groups, and it just turns into a very accessible way of dividing a large site up, because a drone can only fly for, well, a rotary drone tends to have flight times of half an hour, 45 minutes. Biggest site in our fleet is 2 kilometers long by 1 kilometer wide. You're not going to do that in a single measurement. You have to break it up and divide and conquer in that at that point.
Yeah, I agree with you. And what we generally try to do in advance is obtain these flight paths, as Peter was mentioning, and discuss them with operators to understand if there are any interferences with the operation, and also further risk that we maybe didn't account for at the beginning. So to be sure that we can operate in the way we are thinking from the offices, and to understand if there are any other risks in operating this way. I don't know, Brian, if you identified any other question that you like.
Absolutely. Nor asked, besides drones, are there any other suitable technologies for site level measurements for offshore platforms?
Well, again, I guess it comes back to that point about it's about defining the method, and the drone is a very practical means of moving your sensor in the vicinity of the plume. But you could equally credibly, and we've certainly sponsored research projects where people have put similar sensors, and in some cases far more precise sensors, on research aircraft. And so an aircraft is effectively doing the same work as the drone is, more often than not, because of safety considerations and just the size of the aircraft. They have to operate from further away, but perfectly credible to take a measurement from aircraft, and there are service providers that do that as well. It's just a different set of things that go into the method. And of course, if you've got a research aircraft, you can have a sensor that weighs many kilos, as opposed to what you're fitting on a drone where you're limited to maybe 2-3 kilos max. So again, it's the combination of those factors. Sorry, Camilla, I think I cut you off.
No worries. I agree with you. And we also tested some satellite technologies that are way different. But of course, as Peter was saying, there is no silver bullet. So it depends still on the facility and on the specific technology. What I can say about satellite is just that, as Peter was mentioning, the drone can go very close. The aircraft need to stay a bit far away, while the satellite is very far away. So generally the detection threshold is quite high, and also the uncertainty in terms of quantification in the end is still less precise than aircraft and drones. So there's multiple methods, but still depends a lot on what you need to monitor and with what precision and the amount of methane you expect to get.
Thanks so much, Camilla. Are there any questions that you would like to answer?
Just looking at the ones in the chat, I can just so we cover a range of different sort of applications. I can see one from Mark Davis that says, can you comment on methane emissions associated from flares? Have you been able to correlate emissions and drive towards combustion efficiency? And I think the interesting thing about the point you raised there, Mark, is, as I said at the start of the presentation, the aerial emissions or aerial quantitative emissions have multiple applications. The one that is getting the majority of sort of discussion time and has probably dominated the conversation today is around people looking to do site level quantification driven by things like OGMP level 5 conformance. But of course, quantitative measurements by drone can also be used as part of a targeted campaign to understand specific sources, flares being a very good example. In the case of a flare, it's worth bearing in mind that if you have any kind of dispersion model that your drone is working to, the uncertainties are relatively large. So I think the figures that tend to get bandied around a lot in this space are sort of plus or minus 30% is the typical level of quantitation uncertainty. In the case of a flare, if you're only measuring the methane, and you're trying to understand the combustion efficiency, you've then got a drone measurement with a large uncertainty that in turn you then have to compare and contrast to all of the things that went into your other flare measurements. So that would be the flow to the flare, the composition of the gas, and of course, most significantly, how you're choosing to measure destruction and removal efficiency. It can be done. And it can be done very well, but you have to factor that uncertainty into your analysis of the data. Having said that, there are also aerial measurements where people are taking dual sensors up. And I think if there's anybody from Total online, I think they've presented some very good work in this space, where you're measuring, not trying to do a full quantitation of the mass, but you're measuring the ratio of methane to CO2. And that can give a very good indication of how the flare is performing in terms of its combustion efficiency. Although I would say that the exam question in that case, from a reporting purpose, is the destruction and removal efficiency, where you're looking at the hydrocarbon, the CO2, and you also want figures for the carbon monoxide and the soot. And those are much harder components to measure, particularly the soot. So as long as you understand the correlation, or what you consider the correlation between combustion and destruction, then drones can provide a very credible path to understanding how a flare is performing. It's not something that we in BP do because we've elected to use alternative technologies. I think one of the big drivers behind that is when you look at what puts flares under stress and when their efficiency is most likely to be compromised, one of the biggest drivers of that is high winds, and particularly winds that get above about 15-20 meters per second. Those are precisely the conditions in which you're not going to be able to put a drone up in the air because it's just too strong a winds for them. So yes, you can. Personally, we don't, but there has been some great work done by others to look at combustion and destruction efficiency using aerial quantification. do we have in the deck?
Felipe Cardoso Saldana asked a question. Do you use two-dimensional or three-dimensional anemometers for collecting the wind data on the ground?
I can start, but as Peter was mentioning, it still depends on how the technology provider that we selected decide to gather data. I think that what we did was like a three-dimensional wind data, and they combine it with what is on the drone, so with the double quantification, as I was mentioning before. But it's depending on the specific provider that we select for the activity. I don't know if Peter has something to add on this.
I mean, you're spot on that it is very vendor specific at the moment about exactly how they measure wind speeds. One of the things that hasn't come up in conversation so far that is particularly important for people dialing into this with a particular interest in offshore settings is anybody that's looked at sort of air column structure offshore, is it is invariably much more complex than you will often find in an onshore setting. And in particular, where you get sort of boundary layer effects, where the wind speed close to sea level may be very different to what occurs higher up the plume, if you like. And certainly some research where plumes have sort of failed to cross boundary layers and then disperse further than they otherwise would do. So knowing what the wind speed is around your facility and not a single point measurement, and recognizing where you might have wake effects, turbulence, boundary layers, all of these things go into the mix in terms of actually being able to interpret your data adequately.
Thanks, Peter. Here's another question. Can you please name pros and cons, aerial versus QOGI stationary cameras and methane detectors around site perimeter from OGMP 2.0 perspective?
I don't know, Peter, if you want to start, and I can later, whatever you prefer.
More than happy to. Okay, so this question's really around the use of sort of fixed and stationary cameras for doing measurements as an alternative to doing downwind measurements. And a bit like we were saying earlier, in the world of methane, that there is no perfect solution. The great advantage of any kind of stationary camera is, of course, that it is operating continuously. And where we're looking at time-bound variations in emissions, that continuous track has its advantages, particularly in an offshore setting, of course. If you're trying to do some sort of camera-based technique, you need to be able to position your camera so it can see your whole facility. And it may be that there is nowhere that you can position that camera that gives you that complete overview of the site, or where you lack line of sight to principal sources of releases. But you do have that continuous element. So there are advantages and there are disadvantages. And I don't think there is a single answer as to whether or not one is better or worse. It's what's right for you. What's definitely true in the case of quantitative OGI techniques is just like the conversation we were having a moment around standardization for drone measurements. They are new as well. And what goes into a good measurement and how you demonstrate the accuracy and traceability of your method is equally emergent at the moment. And all the same things that are going to need to be put in place ultimately to give people the quality assurance they seek are also being worked right now. And I think the landscape will look very different in a couple of years' time. Camilla, what's your experiences of QOGI?
So yeah, I agree with you with what you said about the difference between the stationary solutions in general and with the drones. So that's what I said also in the presentation. Drones are spot measurement. So you catch a single moment in time, while if you install something that is always there, you get maybe a better idea on variability, but still the definition of the perfect spot to install QGI or a camera, it's hard to find. Also, not just because maybe you don't have a direct line of sight to something, but maybe if you put it at height, you can see most of the site, but at the same time, maybe you have kind of interference of plumes from different equipment, so it's complicated to evaluate the single emission of one equipment or component. So there is kind of a shadow from another component. An alternative solution that is emerging is based on fixed sensors that are generally installed on grids. So basically you can install more than one and kind of create on a perimeter of operational unit or the entire site, this on the fence line, for example. So you have an entire grid of sensors, but still they have tripods or they are installed low. So maybe you don't get to catch the emissions that are above a certain height. So I fully agree on the fact that we don't have a solution for everything. We need to select the perfect solution depending on what we want to see.
Thanks so much, Camilla. We still have a few minutes here, so I think we can address a few more questions. Erwin asked, in order to reduce uncertainty, is it practicable or possible to calibrate sensors prior to data acquisition?
I think this question is interesting because we have two levels of, I think, calibration or something like that, because on one side, we need to calibrate the sensor to be as precise as possible in terms of quantification, so we can see even very low levels of emissions. And that's, I guess, more on provider side, the calibration of the sensor itself. What can be done on drones, or what mentioned Peter before, is that we need to create kind of a calibration world that is upwind with respect to the area that we want to monitor, to get kind of a background concentration, so we are able to distinguish what we are actually emitting in the area that we have selected and identified, and we are sure we are not quantifying or capturing or accounting for that is outside of this boundary. So I think more than the calibration to be as precise as possible, it's important also to get kind of a background level of what we can find if we are not emitting. And then you need to see what your emission add up to this level.
Yeah, and I think we're coming out of the era. There was a very exciting era in the early stages of this, when there was lots of new and exciting sort of university type startups and sort of companies breaking away and delivering new services in this space. But we're coming out of that era, and I think in terms of calibration of the sensor, we're certainly seeing a lot of vendors doing things like getting ISO 17025 accreditation for the actual performance of the sensor, so that they can know what the signal to noise ratio is, which is how well you can differentiate methane above background. And we're also seeing companies starting to get sort of very basic methodology accreditation, sort of 9001 type steps, that shows they have set procedures and they know the limits of their method, and they don't offer services beyond those boundaries. And now the next generation will get more precise beyond that. But yeah, the calibration of the sensor is step one, and then it has to roll up into the wider method as well.
Thanks so much, Peter and Camilla. So we have 2 minutes left, and perhaps we sort of wrap things up with a broad question, perhaps that you both can touch upon. So looking back on your own journeys using Downwind technology, what's one key takeaway for operators who might be early in their own journeys?
I think that it's not there is not
question.
just one suggestion, but I think that the most important thing is knowing what to expect from your facility in order to select the suitable technologies to do your measurement, and so that when you go there and take your measurement, you kind of know what to expect and how it can vary. So you also talk with your people on site to understand what may change in time and what is happening while you do your monitoring activities. So once you need to see the results of your monitoring activity and evaluate how to report them, you already know what you were expecting and what was happening. So I think this is central to understand what you were expecting and how to use your technologies.
I agree with you wholeheartedly. And my only add I'd put to that is, yes, there's work to be done. This is still a new area of development. We're learning how to do measurements, how to get the most out of them, how to plan, how to deploy. But any measurement we take improves our understanding of facilities and understands what goes into a good measurement and what good measurements do we need to take. And just by starting out on that journey, even if your quantitation is not as good as it might be in maybe 4 or 5 years' time, it will tell things about your emissions and tell you things about your facilities, which is the pathway towards mitigation. And ultimately, this isn't an accounting exercise. This is measurement to drive good business decisions to bring methane emissions down.
Hey, Peter, Camilla, thank you both for joining us today. I think we had really excellent dialogue with the audience and very high quality presentation. So again, very grateful for your time. And to the audience, keep your eyes peeled on MGP's website for this recording and updates on the next webinar. Thanks everyone, and hope you have a great rest of your day.